I did turn it on. I think I can hear myself. It's working, right? Okay. All good?
Yeah.
Okay. Yep. Yeah. Thank you very much for the invitation and for the organizers for organizing this workshop. It has been a lot of fun so far. Yeah. The plan of the talk is roughly the following. So, well, in this audience, I think I'll give a very brief introduction of the relation between chaos and black holes. Then I will make some general comments about the connection between gravity and spin structure that will be maybe something everyone knows, but maybe you didn't think about it in too much detail, so it will be helpful for the rest of the talk. And the main part of the talk will be a discussion of fermionic versions of pure 3D gravity dual to ensembles of 2D CFTs with fermions. And in the last part, I will discuss what happens in gravity when you add topological field theories of the type of those that appear in, for example, the discussions about SPT phases of matter, but we will apply it to gravity. And this is based on a paper that appeared a couple of weeks ago with the two students, Jan Boruk from Berkeley and Elisa Tabor from Stanford, and all of the new things I'll describe are from this paper. Yeah. Okay. Okay, so we believe, I think everyone here, that black holes are ordinary quantum systems, and they have a large number of degrees of freedom and that are strongly interacting, so we expect the microstates to display some form of chaos. Universally, there is this double cone geometry that was discussed yesterday by Jonah that captures aspects of level repulsion in the black hole microstates, which is essentially a identification of the Lorentzian black hole. This contributes to a partition function with two boundaries, with length in the time circle beta plus it and beta minus it, and in the random matrix answer, that would be the benchmark of quantum chaos. It has this linear in T behavior with this coefficient 4 pi beta, which multiplied by 1 if you have a GUE ensemble, and 2 if you have the orthogonal or the symplectic ensemble. In higher dimensional gravity, this factor of 2 comes from gauging CPT. Okay, but I will discuss this in more detail in the context of 3D, anyways. So this level repulsion and this chaotic behavior of the system is believed to be universal, and I think one motivation for this program is to try to understand if there is a more refined notion of this universality that incorporates the symmetries of 2D CFTs. Okay. So a promising direction, inspired by the duality between 2D gravity and random matrices, is to define an ensemble by trying to solve pure 3D gravity. Now, defining pure 3D gravity requires fully off-shell geometries, I believe, at least. So this was mainly proposed in a paper of Kotler and Jensen, where they introduce the torus wormhole to reproduce level repulsion. It's a refinement of this double cone to the exact 3D gravity path integral. And in a paper with Maxwell, we also proposed that you need fully off-shell geometries to resolve some pathologies if you try to compute the 3D gravity partition function. Okay, I'm not going to solve this problem of the off-shell geometries today. Instead, I will take the tools we have so far and try to ask the question of what type of gravity theory describes ensemble of fermionic CFTs. So people usually discuss bosonic CFTs or supersymmetric, but you could also have CFTs that are not supersymmetric and have fermions, and you can study what is a good notion of an ensemble of those theories. Okay, before I jump into 3D gravity, let me make some general comments about gravity and spin structures. Okay, there we go. Usually we say, when we talk about gravity and we say we have Einstein gravity, we describe it by saying that, okay, the action is the integral of R, maybe minus 2 lambda if you have a cosmological constant. But this is not enough information to uniquely define the theory of gravity. You also need to specify how local frames are glued together. That's called the structure groups of your spacetime, and you need to define the rules of what structure groups are allowed. So if your structure group is SOD, then you'll have what's so-called bosonic gravity. If your structure group is spin D, you'll have a sum over geometries with spin structure. and you can have unorientable generalizations. And I want to emphasize this is the same as in gauge theories. You cannot truly define the theory until you specify the global forms of the gauge groups. So this is something familiar, but perhaps it's not emphasized in gravity as much. Oops. What happened? Okay. So usually we assume that this choice of the structure group is tied to the matter content, but it doesn't have to be. Of course, the two choices have to be compatible. If you define the theory with structure group in SOD, well, obviously you shouldn't add fermions, or it won't make sense. But and if you have fermions, then you'd better choose the structure group to be spin. But the two are separate choices. Particularly if the structure group is spin, let's say, but you don't have any low energy fermionic matter, you can still have fermionic black hole microstates, which, well, we studied in a paper with Yiming from a couple of years ago. Now, such theories might not have UV completions, but at least it's an interesting implication of doing the gravitational path integral. Okay. And choosing the spin group has two effects. The first one, if we fix the boundary condition, let's say in the context of ADS CFT on some boundary Y, with some spin structure, the first condition is that we should sum over bulk geometries X that have spin structures themselves and they smoothly extend the boundary spin structure to the bulk. This restricts the geometry. Well, the technical restriction is that the second Stiefel-Widner classic has to be 0. Okay, that's just telling you that there is a spin structure. And the second restriction is that only large diffeos that preserve the boundary spin structure should be allowed. And both of these will be important when we do 3D gravity. Okay. But as an example of two, just to show that this is more important more broadly, and this might also be relevant to some of the talks in the afternoon in the context of supergravity. You can imagine a black hole in ADSD with a boundary that is S1 cross SD minus 2. This has two spin structures, R and NS, depending on the boundary condition of the fermion. And we can turn on an angular velocity omega that is 2 pi I over beta, conjugated to rotation in some angle phi. This angular velocity, if I imagine putting it on the boundary metric, it can be undone by a large diffeo of this form, where I shift phi by 2 pi t over beta. Now, if the structure group is SOD, then this is a true statement, and both boundary conditions are equivalent. But if the structure group is spin, then this large diffeo exchanges R and NS spin structures. So then this large diffeomorphism is not allowed anymore. And these two values of omega should really be thought of as different boundary conditions. And again, this is a discussion regardless of whether you have fermions in your low energy matter content or not. And in this paper with Yiming, we point out that this partition function proves how the microstates are distributed according to statistics. It's kind of like a traces with -1 to the F inserted. And this is the type of partition functions that people study in supergravity that we will discuss in the afternoon to compute the index. But the same procedure is true more broadly than to the index for supergravity. One can apply it in any context. Okay. Okay, so if there are no questions, I'll continue with jumping into 3D gravity. Sorry. Okay, so we will study a theory of 3D gravity in which the path integral sums over spin manifolds. We don't want to do supergravity because that would be an ensemble of super CFTs. We want an ensemble of fermionic CFTs, so we just sum over geometries and declare that we keep track of the spin structures and the structure groups are in the spin group. Now, I won't have time to discuss it, but in the paper we also propose a random matrix framework compatible with the symmetries of fermionic 2D CFTs. We extend the RMT2 proposal of, that started with Gabriele Duvaldo and Perlmutter, and it was extended in the last years. We extended to fermionics to the CFT, but that part of the paper I won't have time to cover, probably. Instead, I will focus on what happens when you include anomalies in the ensemble of 2D CFTs and how they are reproduced from gravity. Okay, the simplest boundary is the torus, and the simplest bulk is the solid torus. So this includes BTC, thermal ADS, and their modular images. And their modular images are precisely these large diffeos that I was describing. With a generalization of these large diffeos that I was describing earlier. And then we will also study the torus wormholes, but let's first begin with the single torus boundary and the solid torus partition function. There are 4 choices of spin structures. Now, I said the theory doesn't have fermions, and instead of specifying structure groups and charts, you can just imagine you have a fermion and specify the spin structure by what are the periodicities of this artificial fermion that we introduce. So then we have 4 sectors depending on whether the fermion is periodic or not as you go around the time circle or the spatial circle X. They're parameterized by mu and nu, which are integers mod 2. And these 4 spin structures, on the boundary, they are traces over either the Ramon or NS Hilbert spaces, and either with insertion of -1 to the F or not. So the first question one has to ask is, what is the group of large diffeors that preserves the torus and the spin structure? And this is very simple, but just to remind you, for example, if you pick the boundary condition to be R+, any large diffeor will preserve the spin structure. One way to see it is that you can take the large diffeor parameterized by an SL2 to C matrix and multiply that matrix by the vector mu nu. If the vector mu nu is preserved by the mod 2 is preserved by the multiplication of the matrix, then the spin structure is preserved. Okay, for R-, this would be the Ramon Hilbert space without the -1 to the F. These are the constraints that we have. This is the name of the subgroups of the modular group. And the same for NS plus and NS minus. So NS plus would be Hilbert space NS with the -1 to the F, and NS minus would be the NS Hilbert space without the -1 to the F. Okay. So let's compute the solid torus path integrals. Let's start with the R plus. This is the simplest one because the answer is 0. Actually, the path integral with any number of R plus boundaries has to vanish non-perturbatively. For the solid torus, this is clear because the solid torus is specified by which cycle contracts, but if both cycles are periodic, there is no cycle that can contract at all to produce a smooth bulk spin structure. But the result is more general, and maybe it's useful to phrase it in the language of Bordisson groups because they will appear later. The Bordisson groups is the group of all geometries and spin structures identified where 2 geometries are identified if you can find a 3-dimensional one that interpolates between the 2. Okay? So the Bordisson group for 2-dimensional spin geometries is C2, meaning that there is a component that is trivial, namely can be filled up by a 3D geometry, and a component that is not. R plus is a boundary that is in the non-trivial component of omega 2 spin. These components are distinguished by a mod 2 index. It's also called the R invariant, and for R plus is 1. And for, well, the trivial component should be 0. Right? So more generally, even more generally than for the torus with R plus boundary conditions, whenever you have an odd number of boundaries, could be of any genus, whenever you have an odd number of boundaries with an odd spin structure, the bulk path integral has to vanish because there is no 3D geometry that will reproduce that boundary. So this is an example of the case 1 earlier, where if you declare that the structure groups are in the spin group, then there are geometries that just disappear, even though if you ignore the spin structure, there is obviously a geometry that would appear. Okay, so the remaining 3 ones have trivial invariants, so they are non-vanishing. For the solid torus, you can all fill them up. And the building block is the path integral of Maloney-Witten on each individual torus, which is this is a one loop exact calculation around the solid torus, which is given by the vacuum character, which I wrote here. And this is the result when the spatial circle, in my conventions, this is the result when the spatial circle is the one that contracts. So for thermal ADS. So let me write down the answers. So in the NS plus sector, we have ADS. The spatial circle can contract because the spatial circle has antiperiodic boundary conditions. So we have the vacuum character, and we sum over all modular transformations restricted to this subgroup of SL2C. Now, as explained in the fairy tale paper, not all modular transformations produce different solid tori. To specify the solid torus, we need to specify the cycle that contracts, but then the one that doesn't contract is ambiguous. This ambiguity appears because we sum over these modular subgroups mod C, where mod C is left multiplication by even powers of t. In bosonic gravity, you will have any power of t. Now you have even powers of t because you should make sure that you preserve the spin structure when you. Okay, so then you have the same for ns minus, just the group changes. And for R minus, thermal ADS doesn't appear anymore because the spatial circle has periodic boundary conditions. But instead, we can construct the answer by starting from BTC, which is just this vacuum character with an S transform, and summing over these modular subgroups of the path integral over BTC. And now, this identification is slightly different, but it's the same idea as in the first two cases. Just to remind you some basic facts, these three partition functions are not independent for any 2D CFTs. At the level of gravity, you can see that this is the subgroup connected to NS plus, and this is the subgroup connected to NS minus. The two are equal up to conjugation by T. This is easy to check. So this implies that the partition function with NS plus as a function of tau is equal to the partition function with NS minus at tau plus 1. And shifting tau plus 1 is like inserting e to the 2 pi I j. So this proves that in the NS Hilbert space, there is a spin statistic connection that -1, the fermion parity is connected to the angular momentum in this way. Now, this is not true in the Ramond sector. In the Ramond sector, actually, the partition function is invariant under tau goes to tau plus 1. So all states in the Hilbert space have integer spin, while the partition function with the -1 to the f is 0. So then there is no spin statistic connections in the Ramond sector. And this makes sense if you think of a free fermion. The mode expansion of a free fermion have even integer, even though they are fermionic, so obviously, but the dual of gravity shouldn't be a free fermion, but at least it's a similar phenomenon. So the Hilbert space is, in NS Hilbert space, decompose in sectors of fixed J, where whether it's fermion or boson depends on the parity of 2J. And in the Ramond Hilbert space, you need to explicitly separate the bosons and the fermions because they are not distinguished by J. So all these small details are important when we look at the wormhole and the level repulsion and all that. So that's why I'm going over it a little slowly. Okay, so let me present the leading spectrum from gravity. Now, although the building block is the same as bosonic gravity, is this Maloney-Witten vacuum character, the sum over modular images is different, and that will change the spectral density. So this is one non-trivial way in which gravity spin structure can affect the answers.
All these sums are divergent.
Yeah, in exactly the same way as in Maloney-Witten. Yeah.
So do you have a specific representation in mind?
Yeah, you can do the same one as what they do. I guess they do some kind of zeta function organization. Yeah. Okay, so we can describe the answer in terms of these spectral densities. In the Ramond sector, we need to separately give the bosons and the fermion. In the NS sector, we don't need to. The fact that the gravitational path integral with an odd number of R plus boundaries vanish indicates that, well, first, these rows, the spectral density of bosons and fermions are equal on average. They don't have to be equal member by member, but at least on average. And also that the probability distribution of the Hamiltonian in this bosonic and fermionic sector has to be symmetric under exchanging the two. If we were doing random matrix theory, you would say that they should be statistically independent for a chaotic model, but that won't be true for 2D CFTs ensemble. Okay, and the density of states looks like this. So this is thermal ADS. It's only in the NS sector, and then you have the continuum above the extremal threshold. In the Ramond sector, you just have integer spin. In the NS sector, you have integer and half-integer spins. And here I point out that there are some spins where the answer is negative. It has this famous 1 over square root h threshold behavior with a negative coefficient. This was pointed out in mainly this paper by Oguri, Benjamin, Shao, and Wan a while ago. Now, sometimes this is phrased as being a problem because it's negative. I would like to, at least based on discussions with people. I would like to stress that even if this coefficient was positive, the fact that this is a 1 over square root is already inconsistent with random matrix theory. You would expect the square root edge given the symmetries, not a 1 over square root edge. And these off-shelf geometries that we propose with Henry, they resolve this and turn this not only into something positive, but also with a square root edge. I believe all the other proposals to resolve this negativity, they solve the negativity, but they don't fix this 1 over square root edge, which I think is worse than, or it's as bad as the negativity. Yeah.
These geometries, you have other corrections, and you have to sum a bunch of things to resolve this. Right?
Yeah, I didn't have the details, but one can do the same that we did for these geometries with spin structure and turn these 1 over square root edges into square roots with shifted extremal energies. Yeah, so that part I didn't describe because it works exactly the same way. Yeah. Okay, so let's move on to the solid torus. The two-boundary torus wormhole. So this is the one that Kotler and Jensen studied first in 2020. So we consider the simplest geometry, a boundary with two torus connected by a torus cylinder. Tau 1 and tau 2 are the moduli of the two boundary tori. And this is, just to emphasize, this is a fully off-shell contribution. It's not connected to any solution of the Einstein equation, as opposed to the solid torus. We will follow the procedure that Kotler and Jensen proposed. Depending on who you talk to, this might be more or less controversial, but I think it gives answers that are very reasonable, so I will just assume that I will just follow their approach. But one motivation of the part of our paper that I won't get time to discuss is that both the bosonic and the fermionic results can be reproduced by this RMT2 introduced in this paper. So this is another piece of motivation that this is a good quantity to consider. Okay, so let me briefly review the bosonic answer. So the gravitational path integral on this torus times an interval is given by this. It has few pieces. This is the path integral around the singles T2 cross an interval. This is the analog of the vacuum blocks in the solid torus. Then we have a sum over relative modular images. This is the relative modular image between one boundary and the other. Notice that here is the full modular group that appears. It's not modeled by a action by T or anything. And then we have a factor of 2 that, well, Kotler and Jensen didn't add, but it was realized by Cynthia Yan, that comes from a gauge in CPT, where you have a torus where, as you go from one boundary to the other, you can think of as having some sort of domain wall in the middle that as you cross it, you act with a CPT transformation. This doesn't change the perturbative analysis, but it adds another geometry with the same contribution, so that's this factor of 2. If we take the double cone limit, namely this large times limit of this path integral, then we get the same answer as in the random matrix theory, but multiplied by this factor of 2. And this turns so if you do only this sum, you will get T over 4 pi. This is the GOE answer. But when you add this factor of 2 from gauge in CPT, you get the GOE answer. And this makes sense because CPT squares to, well, sorry, here I call it RT. RT is the name of the symmetry implied by the CPT theorem. Okay? There is this discussion about for it to work in odd dimensions, you need to not use the parity, but the reflection, so it should be RT. So I would just call RT the symmetry, that the universal symmetry implied by the CPT theorem, if that makes sense. Yeah, so according to the CPT theorem, this RT symmetry squares to 1, so you should get the GOE ensemble in all sectors. Okay, so this is the bosonic answer. This is the Kotler-Jensen corrected by this factor of 2. Okay, and then we computed the answer for fermionic gravity. So there are 2 changes that are added here. The perturbative calculation is the same, but now the modular groups are different, and they depend on the spin structure on each boundary. And like I showed with the density of states, the fact that the modular sums are different actually changes the answer. Though here it looks like a mild modification, the final answers will change. And finally, there is also a factor of 4 because besides gauging CPT in the bulk, we also gauge fermion parity. And namely, we have another torus wormhole where if you parallel transport the fermion from one boundary to the other, it picks up a minus sign, plus or a minus sign. So then you have two saddles with different bulk spin structures that you need to sum. Okay? So instead of a 2, you have a 4. And also another difference is that some wormholes vanish. For example, if one boundary is R plus and the other one is NS minus, then this vanishes because if R plus has periodic boundary conditions on both circles, there is no way to smoothly interpolate it to another one where one circle is anti-periodic. So some wormholes vanish, and the ones that don't vanish are given by this formula. And this was also studied independently by Jensen and Newton. I think their motivation was not the same as ours. It was to do supergravity, but they had similar results.
Do you give an interpretation just in terms of spectral statistics of CFT2, what some of these vanishing wormholes means? Like,
yeah, it means that there are some sectors that are statistically independent and some that are not. Yeah. In the RMT1 limit, all the sectors are statistically independent, but in the 2D CFT ensemble, they're not. For example, R minus and NS minus are related by an S transformation, and that's telling you that the two Hilbert spaces are not independent because they're related by modular transformation. In this case, with R plus it vanishes because of this fact that all the wormholes with odd number of R plus boundaries vanishes, and it's the symmetry between the probability distribution of the bosonic and the fermionic sectors of the Ramond Hilbert space. So that's an exact statement, but there are correlations between the NS and Ramond sector. Yeah, but the correlations are what's implied by precisely this formula. So you can derive it from these formulas. Okay, instead of trying to analyze this formula, yeah.
I think people argue that when you do the sum over all three manifolds, you need to also include a cusp manifold.
That's a way, I think, if I know what you have in mind, I think that's the way that Douglas proposed to,
yes.
Douglas and Cynthia proposed to regulate
the sum, yeah, that's right.
Yeah. We didn't try it.
I see.
But that would be nice to check that one gets...
Well, I guess you could have cusps. The reason I asked is because you can have cusps with all the various boundary conditions. And
for the fermions.
Additional contributions, yeah.
Yeah, that would be interesting to check. We didn't do that. Yeah.
Is the cusp an alternative to this zeta regularization, or is it?
Yeah, that's why, I think that if I remember correctly, that's why they proposed it. It's like a physical, it's something you do in gravity that implements the regulator.
Okay.
Yeah. I think so, right? Okay, well, I don't know.
Principle should give you the same thing that you did with the zeta.
Yeah, but I don't remember the exact conclusion in their paper, so I don't want to say something that is wrong.
Cusp has extra choices.
Yeah. So it would be interesting to check. That's a good point. Just saying that I didn't do it, so I don't want to speculate. Okay, instead of analyzing the full answer, let me just take this. I will use this double cone limit to try to make the answer more intuitive. So if we take the double cone limit in the NS Hilbert space, we get this. So this is the GOE answer. And this is fine. On each, RT commutes with -1 to the F, so RT acts on each blocks of fixed J and fixed fermion parity. And fermion number is just taken care of by the fact that J is sometimes integer and sometimes half integer. So this is what you will get from a random matrix ensemble with the -1 to the F and time reversal, let's say. Or not time reversal, but the anti-unitary symmetry. In the Ramond Hilbert space, you get this. So you get the GOE times 2, and the reason is that in the double cone limit, the bosonic and fermionic blocks in the Ramond Hilbert space become statistically independent, and they both contribute with an extra factor of 2. But the nice thing is that you always get the right factors of 2 and the right signs, as we will see later, from the same formula. So, anyways, it comes from this modular sum being different in different sectors. Okay. Okay, so in the last part of the talk, I will discuss what happens when, well, there is a rich structure of anomalies in fermionic 2D CFTs, and we would like to match it with gravity. Well, okay, like I just said, fermionic 2D CFTs have non-trivial anomalies. They involve sometimes fermion parity, time reversal, etc., depending on the case. So what do we have to do in the back to reproduce these boundary anomalies, or what are the ensembles of fermionic CFTs when these anomalies are present? And the new ingredient in the back will be a topological field theory that is classified by cobordism groups. So it's not the most general topological field theory, it's that one that is invariant, cobordism invariant. And it will modify the gravitational path integral in a result that one can exactly match with the boundary anomalies. And this might sound similar to the discussion in SPT phases of matter, but the way we use this topological field theory is slightly different than the way they appear in those. So it's not obvious that the match that I'm about to show you had to work, at least to me. Okay, and a version of this question in 2D gravity was studied by Stanford and Witten, and the idea was try to extend it to higher dimensions. Okay, so let me remind you, well, what I just said earlier. So before talking about cobordisms, let me talk about bordisms. So these classify D-1 manifolds by whether they are equivalent in D dimensions. They can be connected in D dimensions, like I said earlier. I already gave you this example. And these groups are always, different components of the groups are distinguished by invariants that depend on each case. In the case of 2D spin manifolds, is this mod 2 index of zeta, or the ARF invariant. And the first way we will use it, that it already appeared earlier, is that it makes non-trivial constraints on quantum gravity, because surfaces, in general, any surface that lives in a non-trivial class of the boundary cobordism group has to have a vanishing amplitude. So this happened already with these R plus boundaries, but it's a more generic feature. So knowing this is useful to determine which amplitudes are zero and which ones are not. And just to introduce the notations here, I mean the bordism group with whatever structure you have, could be spin, pin, I don't know, SO of dimension D-1, and this argument just indicates whether you have some gauge field living on the surface or not. If it's a point, it means that there is no gauge field. Okay, so we will discuss the more interesting cases regarding anomalies will be in unoriented 3D gravity. If you have fermions in an unoriented spacetime, then you have to be able to introduce a so-called pin plus or pin minus structures. The pin plus and pin minus are distinguished by whether a reflection squares to 1 or -1 to the f. Okay? And whether a pin plus or a pin minus structures exist is classified by a different topological object that I wrote down here. Well, for pin plus is the same W2 as for spin structures, but for pin minus is slightly different. And the relevant bordism groups that will appear that appeared in the paper, and maybe in the rest of the talk, depending on how far I can get, is the bordism group for pin plus. This is C2. This is similar to the one for spin structures. Pin minus is C8. There are 8 components. And then we will also see what happens if you have a C2 gauge field in the bulk. So then, in this case, it's C2 cross C2. In terms of this question about the amplitude with R plus boundaries, the pin minus case is similar to the oriented one. Any manifold with a known number of R plus boundaries has a vanishing amplitude. The pin plus case is a little different. Now the R plus geometry lies in the trivial class of pin plus. Actually, any orientable surfaces is trivial. One can check this by computing this invariant that tells you whether you are in a trivial class or not. And for example, a simple field in the R plus case is given by the Moebius strip times S1. So this has interesting consequences for the ensemble, because now the probability distribution for the bosonic and fermionic blocks are not symmetric anymore for the unorientable pin plus sums. Yeah. So here this is true for any, well, in the case of orientable surfaces with spin structures, all these amplitudes would vanish. but now they don't have to anymore by including these three-dimensional unorientable geometries. Okay, that was Bordism groups. Then cobordism groups classify the TFTs that we will use. So these are TFTs whose partition functions are just a phase. They appear in the literature for a long time in the context of condensed matter, maybe by Kapustin around 10 years ago. And these theories are classified by maps from these 3D Bordism groups to U1. So U1 would be the partition function. These are well defined on closed manifolds, but lead to anomalies in the presence of boundaries. And like I already said, this appears in the classification of SPT phases of matter, but we will use them in a different way. For example, we will sum over bulk geometries and gauge fields and all that. That's in this discussion, that's not done. There is usually a fixed three-dimensional space or gauge field configuration that appears. One doesn't sum over it. Okay, before I discuss, I started at 11:15, right? Yeah. Okay. Okay. Before I discuss the answers, let me give some general comment of how these TFTs can affect the gravitational path integral. Well, first, in the case of the solid torus, we are summing over large diffeos, and the contribution of each large diffeo might be affected by this topological field theory. The way to detect this effect is to, like I said, these field theories are ambiguous on not ambiguous, but they're better defined on closed surfaces. So the best way to compute them is usually to construct a closed surface out of the open one that you have. So if you want to know what is the relative, let's say, partition function on a spacetime with a large diffeo gamma relative to a spacetime without the large diffeo, to compare the contributions from different modular transformations, then you can take your two solid torus and then glue them up to a modular transformation gamma, okay? And then you compute the TFT partition function on this closed spacetime, which by the way is length space, and the partition function of the TFT in length space gives you the ratio of the answer. It tells you how the TFT partition function depends on the modular transformation. The second way that this will appear is when we do this torus wormhole. When we twist by either -1 to the f, RT, or R, this can be, you can think of it as having a domain wall in the middle that as you cross it in the bulk, the domain wall implements some of these symmetry transformations. And this gives you different saddles in the bulk. So this is the standard way which people do it this part is not, well, the new part is to apply it to 3D gravity, but this way of computing these partition functions is standard. So you can, to see, so now you want to compute the partition function, how it depends on the presence or absence of these domain walls. And to do that, you glue the two boundaries. Again, the point is to make a closed surface. You glue the two boundaries, and now you have a mapping torus, where as you go around the circle direction, you act with this symmetry transformation. And the ratio of the partition function with different walls is the same as the ratio of the TFTs before you do the gluing. And this is by the locality properties of the TFTs, because if you compare different partition functions that are only different close to the domain wall, it doesn't care what happens in the boundary. It only cares about the difference between the... So whether you are relating the two wormholes before or after you glue the boundaries, the domain wall doesn't care. The TFT doesn't care, so this ratio is the same. And by the way, this also allows you to compute how the different TFTs give you different phases, also when you sum over modular images on the torus wormhole. So that will appear everywhere. Okay, so in the remaining time, I will describe, I'll see how far I can get. These are the cases we studied in the paper. Oh, maybe I didn't introduce the notation. Let me see. Yeah, so these topological field theories are classified by these cobordism groups, these maps from the Bordism group to U1, and we will call it TP. So the Bordism group is omega, the the classification of the field, or the topological field theories are called TP. This is the nomenclature in condensed matter from topological phases. And there are some subtleties related to the torsion in this definition, but let me just keep it for the purpose of the talk. Okay, so these groups, this TP spin 3, for example, are the classification of these covordism invariants topological field theories on 3D surfaces with a spin structure. And so on and so forth. Yeah. So let me go one by one, and when I run out of time, I'll just stop. Okay. Okay, so the first one is the case for three-dimensional spin structures. It's classified by an integer, and this is just the gravitational Chern-Simons terms in the bulk that I wrote here. And the coefficient, we can call it delta C because, the well-known fact, from the gravity point of view, it's been some nice paper of Krauss and Larsen, that it leads to the differential charge of the boundary gravitons between the left and the right modes, given by, this delta C, by the parameter of this term. This parameter has to be quantized. For spin structure, it has to be quantized by k/2, where k is an integer. For simplicity, since this has, as far as I can tell, this hasn't been studied in bosonic gravity, I'll just give the bosonic answer. In the bosonic case, this delta C has to be proportional to 8 times an integer. So the answer that we propose is given by this, but for the solid torus. So you sum over the solid tori. You have the vacuum character that comes from boundary graviton fluctuations. These vacuum characters now have different left moving and right moving charge. And then this gravitational Chern-Simons term gives you this I won't explain where it comes from, but this phi of gamma is the Rademacher function. And importantly for us, it satisfies the property that if you multiply it by t on the right or the left, it shifts this phi by 1. And this is important because the bulk geometry is invariant under left multiplication of gamma by t. It's this fact that it doesn't matter which, to describe the geometry, you only need to specify which cycle contracts. If you wouldn't have this Rademacher function, this is not invariant under left multiplication by t. Because you have the q to the minus c over 24, you have the q bar to the minus c over 24, but the two c's are different. So without this term, this answer wouldn't make sense. But with this term, when you multiply gamma to the left, this plus 1 here cancels let's say, the anomaly in this vacuum character. But the partition function as a function of tau is not invariant under tau going to tau plus 1. This would be like right multiplication of gamma. Because when you do right multiplication, you can follow the calculation and check that the partition function at tau plus 1 is given by the partition function at tau plus a phase, or times a phase. So this phase is reproducing an anomaly in the quantization, for example, of angular momentum. So angular momentum is not integer anymore, it's integer plus this k/3 shift. Yeah, k/3 shift. The 3 just comes from just the normalization of the delta C and how it relates to this K. Just have to keep track of these factors of 8, there's some factors of 24. I don't know. I don't know any more insightful comment of where it comes from. This Rademacher function also has this property under S transformations, and one can derive that there is no anomaly in the S transformation. And this was studied maybe for different purpose in a paper by Chang and Ling, where they were studying this, how these anomalies affect the modular transformations of the 2D CFTs. But here we can reproduce it from gravity. Okay. Okay, this is the torus wormhole. I will try to be brief. So this is the same as Kotter-Jensen, but now we have to put this factor here in the sum over images, over modular images. This changes the answer completely, but fortunately, in the double cone limit, we still get the universal t over 2 pi beta of this GOE ensemble. And the only effect of this function is that now this spin quantization is not integral anymore. But up to the spin quantization, the double cone is still the same. So. Okay, so now I will discuss.
that formula, so you sum over all the SL2Z, and you have tau1 on the left torus, tau2 on the right torus, and then their prescription is just act on one of the tori with the SL2. But then the classical piece of the Chern-Simons action,
that's associated to the whole geometry as a whole, and that only depends on the single gamma, right? Like it's
Yeah, on the relative gamma.
possible action on this
Yeah.
two boundary wormholes.
Yeah.
And the,
Yeah, you can see it if you compute. This geometry is kind of computing what happens when you do a large diffeo,
Yeah.
and this only cares about the relative large diffeo between the two boundaries.
okay. I see.
Yeah.
If you
glue it together and make it.
cipher,
Yeah.
not cipher.
Yeah. But here the gravitational Chern-Simons appears in two ways, right? One is to produce this change in the central charge, and the other one is to add this phase. Yeah.
Okay.
Yeah.
Yeah.
Although here there is no central charge dependence, so that effect is gone, but you still have the phase. That was tricky. In the beginning, I thought there was no phase, but then the answer doesn't make sense. Okay, let me discuss now a case with unorientable pin minus surfaces. In this case, there is no non-trivial field theory to add, but this will be useful in a minute. The path integral over the solid torus is unchanged. For the torus wormhole, we need to add a new saddle twisted by R. Usually, we just have the RT symmetry implied by the CPT theorem. But if we have unorientable surfaces, it means that we are gauging time reversal or parity in the bulk. So now we have another saddle, which is exactly the same as the one for the spin structure, but where we shift tau to minus tau bar. That's what we do here, of one boundary relative to the other. So this is a saddle where as you go from one boundary to the other, you act with a reflection. But there are no trivial, no non-trivial TFT exists. These two terms just add up without the phase. Yeah, and this is the exact answer, but again, let's take the double cone limit just to get some intuition on the physics of it. So this is what we get in the Ramon sector. I will skip the NS sector. The case in the sector with spin 0 gives you 4 times the GOE answer, and the sector with spin J and J, or J and minus J give you twice the GOE. And the answer is that the Hilbert space now decomposes in this way. So if you look at the Hilbert space at non-zero angular momentum, the parity anti-commutes with J. So parity will not relate sectors of the same. Parity will relate a sector with angular momentum J to another one with angular momentum minus J. So it doesn't act within a single block. So it doesn't do anything. So here you just see the factor of 2. It doesn't do anything other than the fact that now J and minus J have correlation. At spin 0, R act within the block of spin 0. So now at spin 0, you have to decompose the states between bosons and fermions, but also between even or odd parities. And that's where this factor of 4 comes from. But again, these factors of 4 and 2, we are not putting it by hand. They come from this exact answer that I wrote here. So it's nice that it works the way it should in all cases. It always happens in a non-trivial way. Yeah, and this is the algebra that we expect to have. Well, this is the algebra of the generators that would be consistent with the ensemble implied by the torus wormhole. And if you study free fermions, this ensemble is not free fermions, it's of chaotic CFTs. But if you study free fermions, they also satisfy this algebra. So both points of view are consistent. Okay, so let me describe one that is non-trivial. So if you have pin plus structures, there is a non-trivial topological field theory, and the partition function is -1 to the n times zeta. Zeta is the 3D mod 2 index. This is the number of zero modes of the Dirac equation mod 2. And n could be like the parameter of the TFT. That could be even or odd. If it's even, the TFT is trivial. If it's odd, it's non-trivial. And in condensed matter, this n corresponds to the number of fermions on the boundary. That's why I call it n, but there are no free fermions here. But that's just to follow the nomenclature from the original discussions of this topic. Now, this mod 2 index vanishes on all orientable manifolds because they always come in pairs. If you have the Dirac equation, there will be modes with positive or negative chirality on orientable manifolds, and the mod 2 index will always vanish. So all the orientable spacetimes that appear will be unchanged. But now the relevant mapping torus. So here I call x and y the boundary directions and c is the bulk direction. Other than the cases with fermion parity, we have 4 mapping torus where x is periodic, y is periodic, and as we go from c to c+1, as we cross the wormhole, we can act with any sign of or x, either x or y. For example, if the 2 epsilons are +1, we did nothing. If the 2 are -1, we acted with the CPT theorem, symmetry. If one is +1 and the other one is -1, then we act with either reflection or time reversal. Okay, so these are all different wormholes, and these are the mapping torus relevant to compute the partition function. If this product of these indices is 1, then the space is orientable. So if we do nothing and this is 1, 1, then this is orientable. But also if we apply the CPT generator, it's also orientable. This will have a minus here and a minus here. When the 2 epsilons are different, then the space is unorientable, and it's actually the Klein bottle times S1, and the mod 2 index of the Klein bottle times S1 is 1, and this was computed in this paper by Witten in a different context, but that's the answer. So we see at least, we identify one geometry that is affected by this phase of the topological field theory. The resulting two-boundary wormhole is the following. For most spin structures, nothing changed compared to the pin minus. But when you have R plus and R plus, oh, sorry, I should have said, this theta is 1 only when the fermions are periodic on the boundary. Otherwise, they're not going to be any non-trivial zero mode because it won't satisfy the boundary conditions. Okay, so when the two boundaries in the wormhole are R plus, then the two contributions that either have this is the contribution where the epsilon x and the epsilon y have different signs, where you act with either a time reversal or with a reflection. And this one comes with a -1 to the n, depending on this parameter n of the TFT. So if n is even, we get the same answer as for the pin minus. If n is odd, then we get new results. And again, let me focus on the Ramon sector and take the double cone limit. Now the answer vanishes either if the j's are different or if they are both 0. If the j's are non-zero, then the answer is 2 times GOE. If the j's are different, the answer is -2 times GOE. So this -2 is funny, but it can be understood in the context of the random matrix ensemble. So if you look at the algebra of free fermions, just to see the algebra of generators, although we are not talking about free fermions, just the algebra of generators, it will look like this. And then the Hilbert space would be decomposed into the j equals 0 sector, the j different from 0 sector, and the bosonic states of spin j are identified with fermionic states of spin minus j because j anti-commutes with -1 to the f. In the non-anomalous theory, j commuted with -1 to the f. In the anomalous theory, j anti-commutes with -1 to the f. So -1 to the f doesn't act within a block. It relates a block with spin j with spin minus j. And it explains why you get this 2 and the -2 here. Maybe I will not explain it in too much detail, but I can tell you if anyone wants to know the details. But in particular, it explains this weird -2. Okay, the fact that j becomes a fermionic operator. Okay, and in the j equals 0 sector, the bosonic states now. Again, similar to before, this relates to different blocks, but when you look at -1 to the f in the, or j, sorry, in the, or r, sorry, I should have said r also. So r is also a fermionic operator, so it relates j and -j. But it acts, at j equals 0, it acts within the same block, and now the bosonic and the fermionic sectors are identified again. So if you don't add this non-trivial field theory, all the R plus partition functions will not necessarily vanish. But the spin structures always come in pairs, and when you add these phases, those pair of non-trivial path integrals always cancel. So you end up again with this correlation between bosons and fermions that was there in the case of spin structures. Okay, the last example, I'll try to be brief. Is the case where we have spin structures. This is the most interesting one, but it's a little long, so I would just give some general remarks. Is the case with spin structure and a C2 gauge field. On the boundary we have a global C2 symmetry, not a gauge field. The gauge field is in the bulk. And on the boundary, let me call this C2 symmetry -1 to the FL, so we can think of this as having a left moving and a right mover fermion number on the 2D CFT. Now there are 16 torus partition functions because the Hilbert space can be NSNS, NSR, RNS, or RR. And similarly, we can either insert no fermion parity, we can insert -1 to the F, -1 to the FL, and -1 to the FR. -1 to the FR is just this C2 generator multiplied by -1 to the F. You can define it that way. So any C2 symmetry you give me, I can use to define this FL and FR. And the Bordism groups tell us that the objects that appear in this table are the subset of the modular group that are compatible with the boundary spin structure. So the answer in all these sectors will be the sum of the Maloney-Witten answer, but restricted to these subgroups that appear here. And the ones that are in red indicate that they are the boundary spin structure and C2 connection that don't have any three-dimensional space that smoothly fills it in. Okay? And again, I'm not going to do it, but one can, from here, infer a lot of non-trivial properties about the ensemble between different states that are either bosonic or fermionic in either the left or right moving sectors. Now, in 3D, there is obviously no separate left and right moving spin structures, so you should always think of this as 3D fermionic gravity with a C2 gauge field in the bulk. Okay. Now, these non-trivial topological field theories are classified by C times C8. The first factor is just the same gravitational anomaly that appeared before, so I won't study that. And the second C8 is a non-trivial one that is more interesting, and the partition function can be written in this way. Let me just say roughly from this picture how it works. If you have the three-dimensional geometry with a C2 connection A, you need to look at the Poincaré dual surface of A. So this is a surface that could act as a domain wall that implements the non-trivial C2 gauge field. So you look at that domain wall, which is two-dimensional. One can show that any spin structure of this domain wall reduced to a pin minus structure, and then you compute the C8 invariant of that spin minus structure on that 2D subsurface inside the 3D geometry. This is called the Smith isomorphism, and it allows you to compute these non-trivial partition functions of the topological field theories. And the C8 invariant on this pin minus structure, 2D pin minus surface, is the APS invariant of the Dirac operator. But okay, that's just the details of how to compute it. The sum of modular groups, now it is affected by these topological field theories. This was actually computed, well, for the condensed matter perspective in this paper. And if you act with T-square, now this adds these phases in the twisted Hilbert spaces. So now there is an anomaly in the quantization of angular momentum that appears only in the RNS or the NSR Hilbert spaces, but not in the RR or NSNS. So this, here I'm thinking of it as this is the partition function of the TFT on the length space that comes from gluing up to this action with T2. Now, on the two-boundary wormhole, it's a little bit more interesting. Essentially, two things can happen. So this domain wall associated to the C2 connection can be orientable. In that case, the invariant reduces to the mod 2 index of spin surfaces. Or these two-dimensional surfaces, a two-dimensional domain wall could be unorientable. An example is here. So if you do this case where you have the torus wormhole twisted by the CPT, if I have a C2 connection along the y direction, this domain wall would be at y equals 0. But now as c goes to c plus 1, x goes to x goes to minus x, so then it becomes a Klein bottle. So the three-dimensional space is orientable, but if you look at two-dimensional spaces inside 3 dimensions, they can be unorientable. And then you have the mod 2 index. Then you have the mod 8 index. Okay, since Finn is standing up, I assume I'm out of time. So let me just say that we computed these torus wormholes for all these different topological field theories. And we matched the late time answers to the ensemble consistent with the anomalies, which were the algebra of the generators in the cases with anomalies were written down recently very explicitly in some papers by Seiberg and Shao and Shang. All the ensembles appear, GOE, GOE, and GSE. So far, only the GOE one appears. For example, RT could square to -1 now instead of +1, or RT could become a fermionic operator. And we reproduce all these features from the wormhole with this topological field theory on it. Okay, maybe okay, here's an example. I will skip it, so let me just conclude. So we introduce a theory of 3D gravity that is dual to ensemble of chaotic fermionic CFTs. We derive the leading spectrum and statistics. We match the effect from these bulk topological field theories with anomalies in the fermionic CFTs. In the same paper, we also check that these examples fit into this RMT2 framework, but that would probably be a topic for I don't have time to introduce that, but I'll be happy to discuss afterwards. Could be interesting to study also the statistics of OPE coefficients, as in, well, originally in this Berlin de Boer, then Chandra, Kohler, and Harman and Maloney, and then more recently using the Virasoro TQFT, allows to compute this, all the construction of Jafferys and collaborators, etc. All that can be generalized. And let me finish with one question that is, are there interesting higher dimensionals and holographic avatars of this effect? So the object that I need to construct, this mapping torus, one can always construct the mapping torus out of the double cone, just take the double cone and identify the two boundaries. And these non-trivial TFTs exist in all dimensions, so one can wonder if they introduce any interesting effects in higher dimensions. And also how it depends on large diffeos. Well, you can take two black holes and glue them up to a boundary diffeo, and this can affect, for example, quantization of spin or charge quantization, etc. There was actually a recent example studied by Heidemann and Toldo in the context of supergravity, where you can have some theta angles that can drastically change the answer from the naive expectation. So the theta angle could be a simpler example of these field theories, topological field theories. Okay, thank you for your attention.
Any questions?
You said something at the very end about this, and it might have been hidden as well somewhere in between, but is there an equivalent of the APS theorem that can be derived from here, or at all anything equivalent of anomaly descent where all you're doing is just taking in the contributions of gravity as a Chern-Simons term written there?
Contributions of what? Sorry.
Gravity written as a Chern-Simons term. Basically, the story of anomaly descent described here, does that give any intuition at all? Or
Yeah. I mean, that would be cases where you could have a kind of a perturbative anomaly. That's the typical like ADS-CFT case that I guess we didn't discuss, where you can add some like Chern-Simons terms in the bulk. And the closest thing here is the one for the gravitational anomaly. I think these ones are more subtle and they involve global anomalies in general, but it's in a similar spirit.
Well, in this case, the eta invariant would be a cobordism invariant, and you would be able to explain the global anomalies with them, or would?
Well, that's what we are doing in a sense. When you add these topological terms in the bulk and you do the gravitational path integral, it reproduces the anomalies of the dual CFT. Usually you have in condensed matter, I guess usually have a bulk and you have some edge modes that cancel the anomalies. In this case, the anomaly is not canceled, it's just holographic so in that sense it's a little different. But these math theorems about the APS and all that, we use them in the sense that at some point you need to actually compute those phases, and then it's useful to know how to compute them in each geometry, etc.
Does this tell us anything about like including other kinds of global anomalies into the ensemble?
Well, we included at least the ones classified by the cobordism groups. These are all. You could think of other things, like for example, Jensen is studying supergravity. Then in supergravity, you could ask what are all the anomalies and all the topological theories that you could include in that case. But given the assumptions of just having fermions and either time reversal or not, etc., this is well, yeah. At least this is all the things that come out of the cobordism classification. Yeah.
Any further questions? Half the questions from Matt. All right. Well, let's thank Joaquin again.
Yeah.